Hello, gang. Back for lesson 4.4, which is on solving log equations. Yesterday we were solving exponential equations, and sort of the main strategy was, well, there was lots of main strategies, but one of the strategies was to undo an exponential function by taking the log of both sides. And so today, later, we'll see, well, almost in number 2 in the 3-minute review, that we're going to do the opposite strategy for solving log equations. But before we do, good idea is to try one of these, what I thought were the more difficult ones from last day, which is this idea of a common factor. And here, this is a pile of 4s, right? A whole 4, 4, 4, 4, 4, 4, 4, 4, and this is 4, 4, 4, 4, 4, whole bunch of 4s. And so we've got a common factor. The question is how many 4s can I take out? Well, this is a pile of 4s, and this is a pile of 4s, which is the smaller pile of 4s, because that's the most I can take out, is the smallest number, and that's 4 to the exponent 2x. Right? And after I take that pile of 4s out, what's left over? Well, this 2, don't get tempted to try and make this 8, because I got to do exponents first. This 2's got to hang out front. But when I take this, the pile of 4s, 4 to the exponent 2x out, how many are left over? Well, one way I could think of it, I'll do a little work in the margin here, is remember factoring has to do with dividing, like subtract the exponents, right? And so what is it? It's just 1 4, right? And that makes sense. 2x plus 1, there's one copy of the 4 left over. When I take 4 to the exponent 2x out of this one, gone. Then inside here, what do I got? I got 8 minus 1, which is 7. And I'll bet you 7 goes into 1792, because that's going to be the next step here. And it does. I divide by, it's a step, divide by 7 on both sides. And I'm left with 256. And at this point, I could take log of both sides, but hopefully you're starting to recognize some of these powers. This is a power of 4. I just got to find out what it is. 4 times 4 is 16, times 4 is 64, times 4 is 256. And without a calculator, I can write 256 is 4 to the exponent 4. And then I could think of taking the log base 4 both sides, but this is actually, it turned into a grade 11 equation, and I see that the answer is x equals 2. Dandy. And I think that was the hardest ones from yesterday. Today, well, we've actually done ones like this, but we're going to think of them in a different way. We're going to think of, if I want to get rid of log base 2, what operation am I going to do? I'm going to do exponential function base 2 of both sides. And then now I have a function composed with its inverse. They wipe each other out, and I'm just left with x. On the right-hand side, I have 2 to the exponent 4, which is 2 times 2 times 2 times 2, which is whatever, 16. Notice these sorts of things we actually did earlier just by changing form. We just thought, okay, 2 is the base, 4 is the exponent, and the x is the inside thing, is the power. But this idea of the operation on both sides as exponential function will help us solve more problems. Like this one here, exponential function base x of both sides is going to give us, well, a function composed with its inverse. Will wipe each other out. Then I'm just left with 96 equals x to the exponent 3. Now, how do I solve this? Well, I need the opposite operation of a cube, which is cube root, and I can think of that, you know, as 96 to the exponent 1/3. I could think of it this way if I want, or I could just think of it as the cube root of 96, which isn't an even one, right? That doesn't work out perfectly, so I'm jamming this into a calculator. Cube root of 96. If you have trouble finding your cube root button on your calculator, then don't be afraid to ask about that in class. All right, well, there's already some of the stuff that we're doing today. Solving log equations. Solve log equations in one variable using various strategies algebraically. Okay, well, we already did some of that, but notice here we got log based, so we know at some point we're going to do exponential function base 10, but if I did that to both sides right now, and don't write this down because it's going to be goofy, I don't have a function composed with its inverse because there's crud all over the place. I got this 2 in the way, I got a minus here, I can't do it yet. So the idea here is I'm going to do some simplifying first. I got to get rid of this crud. I told you it was crud. There we go, crud, gone. Let's do some simplifying first so that if I had the left side and the right side as just a log base 10, then when I take exponential function base 10, it'll wipe everything out. Well, this isn't so bad because I see I'm subtracting 2 logs. So on the inside, do you remember what the operation is? It's not times because that's a plus. On the inside, it becomes a divide. On the right side here, I've got 2 times, so the 2 becomes up in the exponent. And now, well, now I can see, well, what do I got here? I've got a log base 10 of 2 things. So these things are going to be equal. And in fact, I could think of having the operation exponential function base 10 of both sides, and then I'm left with the inside things. The function composed with its inverse wipes these things out, and I'm x over 4 equals 49, multiply by 4, and I'm going to get 4 times 50 would be 200, but 4 less than that is 196. Dandy. I'm going to pull the same trick here, right? I've got 2 logs I'm adding, so on the inside it becomes what? It becomes multiply. So this is 14 root x. Why did I write it like that instead of the other way? Well, it's just so I realized that the 14 isn't underneath the root. Now I can take exponential function base 10 of both sides. You say, well, hang on, this side isn't a log. Well, do I care? Not really. Because watch what happens. Here, I'm just trying to get x alone, right? I'm just using my equation solving skills, trying to get x alone. So do I care what happens over here? Well, that's 100, right? This is 10 squared is 100. Now I've got a function composed with its inverse on the left side, and I'm left with 14 times the square root of x. And now I'm just solving this, right? At some point, I'd like to square both sides, but not yet because the 14's in the way. Well, what's the operation? I'm going to divide both sides by 14, right? Divide by 14. Dandy. Square root of x is equal to, I don't really care, right? I suppose I could simplify that, but what's the last step? Now I'm going to square both sides. Square both sides is the last step. SBS, square both sides. And I suppose I could jam that into a calculator, or I could leave it just like that, or whatever. I think it's 2,500 over 49, and you can check that with a calculator. A decimal would be okay, but make sure you put that as its approximate answer, and so you're not losing any communication marks. Dandy, onwards. How are we doing for time? 8 minutes. I think I'm just going to charge through, and maybe I only have a 1 video night here. Wouldn't that be fantastic for us all? Oh, see, look at there, not light at the end of the tunnel. This one doesn't look any harder than the ones from the 3-minute review. What's the idea? The idea here is, how do I get rid of this log base x? Well, I'm going to do the opposite operation of log base x, which is exponential function base x. And how does that look? What does that look like? Well, I've got a function composed with its inverse. This part wipes out, and I'm left with just 3. On this side, I have, well, 3 equals x to the exponent 7. How do I handle that? Well, I could do the 7th root of both sides, or I could think of what exponent. I know I want x to the exponent 1. What exponent on both sides is going to give me an x to the exponent 1? Well, it's 3 to the exponent 1/7, right? Because when I multiply exponents, right, this is 7 over 1. I could think of it as 7 over 1. Then multiply across, yeah, that's going to be 1. So this opposite operation, opposite exponent operation, 1/7, and this is the same thing as the 7th root. And you're welcome to put that into your calculator, or you could put the 7th root into your calculator, however it's easiest for you. And if you're having trouble again with these roots, don't be afraid to ask on your ask for calculator help. Probably, I wonder if I have my calculator. I don't have my calculator. I'll pause the video and get my calculator up so I can show you how I put that into the calculator, okay? Right, bam, we're back with a couple of calculators here. And you don't have to use the graphing calculator. The reason why I like showing on the graphing calculator is most of your scientific calculators behave this way. And the idea is, if I want to put in the anythinth root, most calculators will have a cube root or a square root, but the anythinth root, like the 7th root, basically we have to put the 7 in, and then we find an x root y button or something as such, and on the graphing calculator, and you'll have to press shift on your calculator probably, it looks like probably something like that, and the button on your calculator, I'll write what it probably might look like otherwise. So it's like this idea of the 7 goes up here into the root, and then this will be the 7th root of 3, which is 1.17 about. So for most calculators, by the way, it's going to be, you put in the 7, and then you hit probably this button. You might have to press shift first. It also might look like this, maybe, depending on what calculator you got. Then you press 3 and then press equals. If you've got an old school calculator, this process here is backwards. Just like if you got an old school calculator and you're doing trig functions, you put the angle in first, right? You put in the angle first and then hit trig, right? And then it does that. This is backwards too. So I'm going to put in the underneath thing first, 3, and then there's your nth root or yth root button, and then you hit 7 equals. It's backwards for the old school calculator. So if you're not sure which you have, then don't be afraid to ask in class. I probably over-explained that, but that's okay. We only got one example left. So, and this is a good one though. Looks strange. Actually, it doesn't look too strange. It kind of looks like this one. Right? It kind of looks like that one, where we're going to have to do some simplifying first. When I'm adding 2 logs, I know it's adding on the outside. It becomes multiplying on the inside. So this is log base 3 of 2x minus 1 times x on the inside, right? This is times, and that's equal to 1. And then how do I get rid of the log base 3? Well, it's exponential function base 3 of both sides. Exponential function base 3 of both sides. And I'm not scared that this isn't a log on this side, because that's just going to be 3, right? That's just 3 to the exponent 1 is just 3. This cancels out, and I'm left with, something strange. Something strange is afoot in question D here. How do I solve this? Well, this is going to be a quadratic, right? I multiply through, I expand, and remember, since there's 2 x's, I can't isolate it. So this is a grade 10 quadratic. Remember, I need one side equal to 0, and then I'm looking for a factor or formula, right? It's a hard trinomial. I'm looking for the factor formula, and I'm hoping that you're getting better and better at factoring these hard trinomials. I know it's going to be 2x and x, and then I just got to figure out where the 3 goes so that I get minus 1 in the middle. Minus 3 and positive 2, right? Because 2 times 1 is positive 2 minus 3. Yep, that's going to work. That's the right factoring, and I can find my 2 solutions. I got x equals minus 1 and x equals 3 halves. Now, dandy, 2 solutions. Who'd have thunk? Who'd have thunk that I had 2 solutions? But one warning. Have a look. When I put these things back into the original equation, an answer of x equals 3 halves is fine. I put in 1.5 here and 1.5 here. I could try and jam this into a calculator, use the change of base formula, work out the left side and right side, and this one's fine. But when I substitute this back, note, 2 times minus 1, and this is x, right? This is x. An x value of minus 1, I have the log base 3 of minus 3. This is a big uh-oh. Remember, log base 3 is undefined for any values of x that are less than 0. This is undefined. Remember, our trig graphs, here's log base 3. All of them go through the point 1, 1, 0. Log base 3 of x. Look, x values over here undefined. So anything that gives me a 0 or a negative as the input isn't a solution. So we have to check. This is what's called an extraneous root. Our equations, extraneous, I want to spell that right, extraneous root. I have to check and see if the solutions I get work in the original equation. This one doesn't work. So what is my conclusion overall is the only solution is x equals 3/2. Will this always work and I can always discard the negative? No, you need to substitute back and actually check both of your solutions. Okay, believe it or not, I got her all in one video, so have fun. It's lots of bits and pieces, and we're moving quite along in this short exponential and log function units. I think tomorrow we start talking about applications of these sorts of things. So we'll have fun with that, and you have fun with your homework. Don't be afraid to ask about this calculator stuff in class if you're having trouble.